Hello everybody, thanks for tuning in. My name is Andy and I'm making a video on variation of parameters. So, variation of parameters is a technique for solving a special type of differential equation. That type is second order linear non-homogeneous differential equation. What I mean by second order is that the second derivative is the highest we're allowed to take. What I mean by linear is that all we're allowed to have are functional or constant coefficients. And by non-homogeneous, I just mean that the right-hand side, f of t in this case, is non-zero. Something special to notice about this differential equation, the constant coefficient on y double prime is 1. This is necessary for variation of parameters. So if we tried to apply the variation of parameters technique to a differential equation that did not have 1 as the coefficient, we'll get the wrong answer. So if you're looking at an equation like that, you should divide the entire equation through by that leading coefficient so that it becomes 1. That will change p of t, and it will change q of t, and it will change f of t. But at that point, we'll be able to proceed and solve the equation using variation of parameters. Okay, well, the second ingredient we're going to need is a solution to the homogeneous part of the differential equation. So notice over here, I've changed my f of t, which was non-zero, to the 0 function. Other than that, everything else, all of this, has stayed the same. Y double prime, p of t times y prime, p of t times y prime. Q of t times y, q of t times y. So we need that to happen for two different values of I. We need y1 is a solution and y2 is another solution. And the third thing we need in order to start our variation with parameters problem is that the Wronskian of y1 and y2 is 0. And that's another way of saying that the solutions are linearly independent. So basically, if we look at steps 2 and 3 together, all we're doing is finding the complementary solution to the homogeneous part. Some people call this y sub c, some people call it y sub h, but it's the same idea. It's c1 y1 plus c2 y2. That's the most general solution to the homogeneous part. Okay, well, after we've got all that, we can move on to part 4, and this is the variation of parameters formula. This is all it is. It says that a particular solution, y sub p, is given by y sub 2 times this integral minus y sub 1 times this integral. Notice I've dropped the functional notation at this point because writing at t after everything gets a little bit tedious. But keep in mind, all of these things are functions of t. So variation parameters is very nice because it wraps up solving a differential equation into this nice single formula. The catch is that it's not necessarily easy to do these integrals. Now, before I move on, it might be worth mentioning that sometimes this numerator is referred to as W2, and this numerator is referred to as negative W1. So variation of parameters can be stated more nicely if we let the particular solution be u2 y2 plus u1 y1, where u2 is the antiderivative of W2, W2 over W, and U1 is the antiderivative of W1 over W. But really, this is just a way to abbreviate the variation of parameters. At the heart of it, we're always using this formula. Okay, so let's give it a try. Take an example like y double prime minus 4y is equal to t e to the negative 2t. So the way that we start this is by looking at the homogeneous part of the differential equation. So we're going to take just this left-hand side, y double prime minus 4y, and we're going to make that equal to 0. And we're going to solve this differential equation. In fact, we're going to find the general solution to this differential equation. So we could form the auxiliary equation. Y double prime is going to change to r squared. This minus 4y just becomes minus 4. The 0th derivative corresponds to r to the 0. And that's equal to 0. So what happens when that's equal to 0? Well, that means that r has to be equal to either plus or minus 2. We could use either the quadratic formula, or we could just factor this, or this is actually a very, very common type of polynomial, so you might just have the answer memorized. But in any case, we get r values of plus and minus 2, and so our linearly independent solutions are going to be y1 equals e to the 2t, and y2 equals e to the negative 2t. So positive and negative 2 are the values, e to the rt are the solutions. So let's work out the Wronskian of y1 and y2. So remember, we write this as w at y1, y2, and it's given by the determinant of this matrix. So I've gone ahead and filled in these functions. Notice y1 goes right here, y2 goes right here. The derivative of y1 is 2e to the 2t. The derivative of y2 is negative 2e to the negative 2t. And the way that we compute determinants is by taking the product of the diagonals and subtracting the product of the off diagonals. So the product of the diagonals in this case is going to be e to the 2t times negative 2e to the negative 2t, and something very interesting happens there. This e to the 2t cancels with this e to the negative 2t. We're going to see that behavior a lot in this problem, it turns out. But anyway, that product is 1, so all we're left with is that coefficient negative 2. What about those off diagonals? Well, we're going to subtract their product, and what we get is 2 times same thing, times 1. So negative 2 minus 2 is the Wronskian, and this happens to be equal to negative 4. Okay, so now we have all of the ingredients we need. We've got the Wronskian, we've got y1 and y2, and we have f of t. So let's plug that into our formula. And I'm just going to copy and paste from up here. So we'll make it a little bigger so it's easier to work with, and get rid of some of this extra stuff. Okay, here we go. So we just figured out this part here, so these two denominators, the Wronskian of y1 and y2. And those are going to be negative 4, so let's erase that Wronskian notation, and we'll just put negative 4 in the denominator here and negative 4 in the denominator here. Now we also know y1. y1 is e to the 2t. So we can replace this one and this one both with, let's match colors, e to the 2t. e to the 2t. We also know y2. That was another one of the ingredients we figured out. That's e to the negative 2t. So let's make those replacements. We get e to the negative 2t here, and an e to the negative 2t here. Finally, last thing to replace, f and f. And if we look above, we've also got that. That's te to the negative 2t. So let's write that out. That's t e to the negative 2t. t e to the negative 2t. And from here, it's just simplification and a little bit of calculus too. So I've simplified down here a little bit. Notice that e to the 2t times e to the negative 2t, that's equal to 1. And we can take this negative 4 and bring it to the outside of our integral. Same with this negative 4. But when we combine these two values, instead of getting e to the 0, we get e to the negative 4t. Because remember, we add exponents when we're multiplying like bases. So here are the two integrals we'd like to evaluate. This one, luckily for us, is fairly straightforward. This one is going to require integration by parts. So I've got this colored nicely. We're going to let u be equal to t and dv equal to negative e to the negative 4t dt. So let's figure out what du and v are. Well, du would simply be dt. V would be the integral of e to the negative 4t dt, and via probably a u substitution is a bad idea since we're using u over here, but maybe we could do an x substitution. We would get negative 1/4 e to the negative 4t. And once again, to get from here to here, we'd use maybe an x substitution. In fact, we'd use x equal to negative 4t. Okay, so how do we put that to use? Well, the first thing I'm going to do is combine all of this into one term. That goes right down here. This becomes negative t squared e to the negative 2t over 8. So we get t squared over 2 as our antiderivative, and combine all the terms into one fraction, and this is what we end up with. You'll notice I didn't include an integration constant. We don't actually need them when doing variation of parameters. If we included them, what we'd end up with would be the general solution, actually. And right now, we're just after a particular solution. So just to make our lives easier, because forming the general solution isn't so bad at the end anyway, so we're just going to do this finding a particular antiderivative. Okay, so what about the rest? So this ratio, that stays same. That's showing up right down here. Inside parentheses here, I need to put something equivalent to this integral. So what's that going to be? Well, this is the integral of u dv. And I know from Calculus 2 that the integral of u dv is equal to uv, so here's u, times v. Notice, once again, no integration constant needed, e to the negative 4t, minus the integral of v du. So here's v, and du is just dt. Now, luckily for us, this is an integral we've actually already done. So here I'm just going to simplify what's inside of those parentheses a little bit. We're going to end up with, this will become negative t e to the 4t over 4. We've got two negatives here, and that makes a positive. There's 1/4 that can come outside of the integral, and the antiderivative of e to the negative 4t dt is negative 1/4 e to the negative 4t. This gets multiplied by negative 1 over 4 e to the 4t. So, if we multiply all that out and simplify, we're going to get this. And one thing we can notice is that we've got a common factor of e to the negative 2t. If I factor that out along with the greatest common denominator, I can write this very concisely as e to the negative 2t over 64 times negative 8t squared minus 4t minus 1. And this is exactly the form of a solution that we would have guessed using undetermined coefficients. We would have guessed a quadratic polynomial times e to the negative 2t. But variation of parameters gave it to us all automatically. So here is a nice particular solution. A general solution, if we want to press on a little bit further, we could say our general solution is always given by y sub c plus y sub p. So this was our complementary solution, sometimes called y sub h. And we can form that very quickly. Y sub c, that came in two parts. C1 y1 plus C2 y2 and we've got y sub p right here. Actually, let's copy. And we can even replace y1 and y2 with what we know them to be. We know y1 is e to the 2t. We know y2 is e to the negative 2t. And so there we have it. Y sub p is this stuff here. Our general solution to the differential equation is right there.